Unit 5, Video Lecture 4, Molecular Geometry. We've practiced creating formulas for covalently bonded compounds. Now what we're going to do is build off of our original Lewis structures into creating Lewis structures for compounds. So our steps for creating these Lewis structures for covalent compounds is to first understand that if we have a hydrogen or a halogen, they are going to be our terminal atoms because they can create only one bond. If you don't have hydrogen or halogens, so if you don't have hydrogens or halogens, then we're going to go to number 2, saying that the atom with the lowest electronegativity is going to be the central atom, or the inside atom. Step number 3 is to find the total number of valence electrons in the molecule. We're going to determine the number of bonding pairs by dividing the number of valence electrons by 2. Place one bonding pair between the central atom and each terminal atom. Then we'll place remaining electron pairs around the terminal atom to satisfy the octet rule. If the central atom is not surrounded by some combination of 4 bonds or unshared pairs, we're going to need to double or triple bond. And when we talk about double or triple bonding, we're going to talk about sharing more than one set of electrons. So when we talk about a single bond, when we talk about a single covalent bond, it's 2 total electrons, 1 pair, because it takes 2 to make a pair. A double bond, wow, I misspelled bond. A double bond has 4 total electrons, 2 pairs. And then our triple bond has 6 total electrons, or 3 pairs. And we represent them. A single bond would be shown with just 1 line, a double bond with 2 lines, or a triple bond with 3. So let's go through and take a look at ammonia. Ammonia's formula is NH3. If we want to determine our terminal atoms, we have hydrogens. So hydrogens are going to be our terminal atom. So we're going to put hydrogen on the outside. And there's 3 of them. This then makes nitrogen our central atom. Step number 3 is to determine the total number of valence electrons. Well, nitrogen has 5 valence electrons and hydrogen has 3. Hydrogen has 1 valence electron, and there's 3 hydrogens. So we're really talking about 3 electrons. So our total, we have 8 total electrons. So what was our next step? To determine our bonding pairs. So we take our 8 and divide it into pairs, saying that we have 4 bonding pairs. So what we're going to do is we're going to share a pair of electrons between the central atom and each one of our terminal atoms. So we've used up 1, 2, 3 of our 4 pairs. Now that we've used 3 out of our 4 bonding pairs, we're going to place remaining unshared pairs around the terminal atoms. Well, hydrogen is full. It's sharing an electron. So if we look, the hydrogen atom And the nitrogen atom, one of those electrons from each one of those atoms is being shared between it. Hydrogen can't take any more. It maxes at 2. So we can't put any of our extra electrons around any of the hydrogens. So we're going to take our last bonding pair and make them an unshared pair of electrons on our central atom. So these guys are unshared pairs of electrons. So that's our Lewis structure for ammonia. And again, it doesn't matter. It doesn't matter where you put those hydrogens. You could have just as easily put the hydrogen on top. That would be acceptable as well. So when we see this, what we're actually looking at, we have nitrogen That's our Lewis structure for nitrogen, and our Lewis structure for hydrogen. We'll share those electrons between them, and so nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons, making it happy. And all of our hydrogen atoms, this hydrogen atom has 1, 2 electrons. This hydrogen atom has 1, 2, 1, 2. So all of them are happy. Let's draw the Lewis structure for pH3. Again, because we have hydrogen, it's our terminal atom. So we'll put hydrogen on the outside and phosphorus in the middle. Our total number of valence electrons is 8. How did we get that? Phosphorus has 5. There's 3 hydrogens. So that's 3. 5 and 3 is 8. 8 total electrons mean that we have 4 bonding pairs. So 1, 2, 3. And then our remaining unshared pairs should go around the hydrogen, but hydrogen is full. So we then go to our central atom. Remember, we assign unshared pairs to the terminal atoms first. So let's look at NF3. Our first step is hydrogens and halogens are terminal atoms because they can only form one bond. Well, we don't have hydrogen, but we have F, fluorine. That belongs to the halogen family. So our 3 fluorines will be on the outside, with nitrogen being in the middle. The total number of valence electrons is going to be 5 from nitrogen plus 3 from fluorine. So each fluorine has 7, so 5 plus 3 times 7 means that we have 26 total electrons. And this is from nitrogen, and this is from fluorine. So now we are going to determine our bonding pair. So we divide 26 by 2. It tells us that we have 13 bonding pairs. That's step 4. So we'll place one bonding pair. Remember, step 5 is to place a bonding pair. And then 6 is to assign unshared pairs to the terminal atoms. So we'll start here. So we've placed one, 2, 3 pairs of electrons, and let's start here. 4, 5, 6, 7, 8, 9, 10, 11, 12. So we still have one unshared pair of electrons left over, so we'll assign it to the central atom. CCl4. Take a second and try this one. Pause the video and try this one on your own. CCl4. Now let's move on and start looking at creating molecules that have multiple bonds. And the first one we're going to look at is carbon dioxide. Neither carbon nor oxygen are halogens or hydrogen, so our first rule doesn't help us very much. So our second step is to look at the electronegativity. So our electronegativity of carbon is 2.5. Our electronegativity of oxygen is 3.4. So since carbon is the lower electronegative atom, it is the central atom. So we'll put an oxygen here, carbon, and an oxygen. Step number 3 is to determine our total number of valence electrons. So we have 2 oxygen atoms, each having 6 valence electrons, plus carbon's 4. 2 times 6 is 12, plus 4 means that we have 16 total valence electrons. To determine bonding pairs, we divide that by 2, so we have 8 pairs of electrons to place. So we bond our central atom to our terminal atom, and then assign remaining pairs to our terminal atoms. So 1, 2, 3, 4, 5, 6, 7, 8. So now we look. Oxygen's happy because it has 2 electrons here, 4, 6, 8. The right oxygen's happy because it's sharing these 2, 4, 6, and 8. But our carbon atom in the middle is not happy. There are now only 4 electrons around it. So this is where step number 7 comes in. We need to take from our oxygen atom, we're going to take one of the unshared pairs, and it doesn't matter which unshared pair, but we're going to take one of our unshared pairs and have it double bond to carbon. So we take it away from the oxygen and have it double bond with carbon. And we'll do the same thing over here, except this time we'll remove these electrons and create a double bond. Again, it doesn't matter which unshared pair you use to create the double bond. Doesn't matter which unshared pair you use to create the double bond as long as you use the double bond. So now carbon has 2, 4, 6, 8 electrons that it's sharing. So its octet is now full. Let's take a look at SO2. Again, we run into the problem of having no hydrogens and no halogens. So we have to use the electronegativity difference. Now, sulfur has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. Since sulfur is the lower electronegative, it's the central atom, and oxygens are the terminal. The total number of valence electrons, we have 2 oxygen atoms that have 6, and we have a sulfur atom that also have 6. That means we have 18 valence electrons total. Divided by 2 tells us that we have 9 bonding pairs. So we single bond our central atom to our terminal atoms and assign our remaining electrons around our terminal atoms. So 1, 2, 3, 6, 7, 8. So we have 1, 2, 3, 4, 5, 6, 1, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen's happy. So we'll assign our 9th one to sulfur. We have no more pairs to bond, to place. However, sulfur only has 6 valence electrons. So we need to create a double bond. We take a bonding pair from oxygen and create a double bond. Now you may ask, well, what if I didn't want to make that one? What if I didn't want to use that oxygen? What if I did this oxygen? Doesn't matter. They're still the same thing. So either one of these Lewis structures would be correct. Let's take a look at one of our diatomic molecules. If we recall, we had 7 atoms that exist as diatomic. So what would nitrogen look like? Well, since there's only 2 atoms, they're both technically terminal. We determine our number of valence electrons. There's 2 of them. Nitrogen each has 5, so we have 10. Divided by 2, we have 5 bonding pairs. So we bond together for 1, 2, 3, 4, 5. This nitrogen's happy because it has 1, 2, 3, 4 pairs, or 8 total electrons behind it, around it. But this nitrogen only has 1, 2. So we're going to create a double bond. Remove the electrons here. So this nitrogen still has 8. This nitrogen has 1, 2, 3. So this nitrogen still only has 6. Not happy still. So we're going to take another pair of electrons away and share it between it. This now gives both nitrogens 8 valence electrons. So nitrogen is an example of where we see those 3 lines telling us that we created a triple covalent bond. So started to create these Lewis structures, and we've seen that they start to take some particular shapes. And our molecular geometry tells us that when atoms combine to form small molecules, they're going to take on certain shapes that allow their pairs of valence electrons to arrange themselves as far away from each other as possible. Why are they going to want to arrange themselves as far away as possible? Well, you have to remember our electrons are negative, and when we put 2 like charged particles near each other, they want to push away. So these negative charges are going to want to occupy as the space as far away from each other as they can. The shape that this molecule takes is going to affect some of its physical properties, especially the melting point and boiling point of the substance. To describe molecular geometry, we use the VSEPR theory, the valence shell electron pair repulsion theory. This has to do with very small molecules and saying that the valence electrons are going to repel each other due to the similar electrical charges, and unshared valence electrons are going to need the most amount of space, or more space than shared electrons, and this is going to cause molecules to bend and no longer take on a linear shape. So to maximize the distance between atoms that are bonded to a central atom, these molecules will assume 5 common shapes. The first is linear. Okay, this linear model appears in a straight line. The bond angle is 180 degrees. So we saw this with something like carbon dioxide. Nitrogen. These were linear molecules. If we have 2 bonded molecules and 2 non-bonded pairs around the central atom, the molecule will be bent. And the bond angle is close to 105 degrees. So this would be something like if we looked at water, H2O. We have hydrogen being a terminal atom, oxygen being a central atom, bond together, and we would have 2 unshared pairs of electrons on this oxygen atom. These unshared pairs are going to want to occupy as much space as possible, thereby pushing this molecule to bend. We have 3 bonded pairs around the central atom. The shape is what's called trigonal planar. This is a triangular flat shape with a bond angle of 120 degrees. If we have 4 bonds around the central atom, and our molecule is going to be tetrahedral. We saw this when we looked at something like, if we were to look at something like carbon tetrachloride. Carbon would be our central atom. The chlorides would be our terminal. And we have 4 bonds, 1, 2, 3, 4 around the central atom. So that would be a tetrahedral. If we have 3 bonded pairs of electrons and 1 non-bonded pair of electrons, we'd call that pyramidal, with the bond angle at 107 degrees. Now, you're not going to have to memorize these. On the test, you're going to be given, you'll have something to take a look at, but you are going to need to be able to know how to read this. This column here tells you the total number of pairs that are around the central atom. This column refers to our shared pairs, and then lone pairs or unshared. This is also unshared pairs of electrons. And we see our 5 shapes that we're going to need to refer back to. When we talk about the length of the bonds, or how far the atoms that are bonded together are from one another, the larger the atoms we use is going to result in the greater bond length. Because remember, those nucleuses are positively charged. So if we've got a positively charged nucleus here and a positively charged nucleus here, there's going to be some repulsive forces there. So the bigger the atom, the more positively charged it is, the farther away it's going to want to be, and also the larger the atom, obviously the more energy levels it has, because if you remember our atomic radius, so the farther away it gets, the larger the bond angle. If we have more than one bond, so if we're talking about our double or our triple bond, it's going to be a shorter bond length. When we talk about, you may have heard something called polarity or polar molecules. This is determined by the shape in combination with the polarity of each bond. In general, if our shape is symmetrical, it's going to be nonpolar. If it's asymmetrical, our molecule will tend to be polar. We're also going to look at differences in the electronegativity. And the magic number that we're looking for in electronegativity is a difference of 1.7. So, if we look at sulfur dioxide, oxygen has an electronegativity of 3.5. Sulfur has an electronegativity of 2.5. Now, this is a symmetrical molecule, so that would lead us to believe it is nonpolar. However, when we look at the electronegativity difference, 3.5 to 2.5, we see a difference of 1. If it's below 1.7, so 0 to 1.7, we're going to consider it nonpolar. If we have 1.7 and above, we're going to call it polar. So since we have an electronegativity difference of 1, we're going to call SO2 nonpolar. Another note on polarity, make sure that you pay attention to your polar bear and penguins comic book reading. Large molecules can have polar and nonpolar regions. One of the most common examples would be in our cell membrane. We have a nonpolar region in our phospholipid. So our cell membrane is actually made up of phospholipids like this. We're going to have nonpolar regions and polar regions of these molecules. Polar is going to stay with polar, and nonpolar is going to stay with nonpolar. So you can see these head parts of our phospholipids stay together, and the tail parts of our phospholipids stay together. And molecules will tend to shape itself so that polar regions and nonpolar regions are created.